morning. Hello. Hello. NOC 3D. Hello. Hope everyone had a good spring break. Keep moving. All right, so we're moving. We have continued our assignments. So problem set 6 is due, problem set 7 is coming. We'll have a problem session tomorrow. And what you all been waiting for, the next exam. Yeah, I know. Have been on another big day, April 15th, taxes and to Physics Society. What I will plan to do on the 10th, which is the Thursday that precedes this, we'll have a review session. For example, Aisha will be traveling on the 11th.
Yeah, excuse me, sir. This exam 2 now is going to cover from lecture 7 to.
Yeah, so we'll talk about that a little bit more. It will cover problem sets 5, 6, and 7. Okay. But we'll talk about it a little bit more. You don't have to yet start worrying about it. Whatever you say, yeah. Right. Okay. All right. So let's see. So we have been talking about electrodynamics in what we call macroscopic description. Where we're thinking about there's every microscopic charge is described in the system, right? So formally speaking, I can think about, say, the charge density at some position as a function of time is, I sum over every possible charge in the universe. It has some charge, and it is moving in some way, and there is a charge at some position x as a function of t, and this is the charge density, right? And the current density as a function of time is given by the charge times the velocity times the density per charge. So that's a very microscopic description of everything in the universe that is there. We're taking it into account, and of course, we take a kind of continuum limit when we think about a continuous charge distribution. This has delta functions located at every point, but we kind of smooth that out in some notion. But, often we're not really interested in this. We want some more macroscopic description. So just as an example, suppose we were just thinking about the very simple problem of, a capacitor with some parallel plates, and we were to say, I want to know what is the electric field between these two plates that have, some area. We have some electric field, say, so this is attached to this battery, for kind of in 3D. And we treated this as if it's in vacuum, okay? And we calculated, say, what the electric field is. That depends on the surface current, surface charge density that forms with this. But, if we're doing this in air, well, there's other stuff around. It might be a decent approximation. Air is, pretty tenuous as far as the amount of matter that's in it, but there's matter in here. Right, like air. And that matter in the macroscopic world is consisting of an Avogadro's number of molecules. I mean, are we going to write down 10 to the 24th charge configurations in that to try to calculate the total electric field that's coming from every charge in every molecule in air plus that? No, we're not going to do that. We have a more efficient, approximate description. And again, I emphasize, approximations is what physics is about. So how are we going to appropriately approximate the situation so that we can take the collective effect of all the Avogadro's number of molecules that are sitting in there in our macroscopic world to get a good approximation for what, say, the electric field is between these capacitor plates. And so, well, we do this all the time in statistical physics, and the idea is to think about coarse graining. Okay? So what does that term mean? It means there's a sense in which there's something that at the macroscopic scale is fine enough that we can consider it to be effectively a point. But at the microscopic scale, it's coarse, okay? So that we can think about the ideas. If I have some material here, this might be a block of air, or maybe it's a block of of glass, or maybe, you know, it's a silicon oxide layer, and there's, you know, here's the origin that I want to think about in my coordinate system, and, you know, there is a coarse grain. It has some volume, little volume, delta V, and delta V is coarse in the sense of that it's much bigger compared to, say, the size of a molecule, but much, much smaller than the size of variation in the macroscopic properties. This is very vague. And one has to then think about, you know, the fact that there are going to be some microscopic fluctuations and how big those fluctuations are and how much those fluctuations affect what we see at the macro scale is something we'd have to consider in terms of what detail of information, what sort of signal to noise we actually would care about, okay? But at the end of the day, this is something that isn't a rigorous, oh, this is the size of the coarseness that we want. It would be tied to the degree to which the precision we care about that would come from whatever fluctuations arise from this finite coarse grain. Yes?
Is delta V the difference between the origin and that circle pit?
No, it's the size. Delta V is the volume. This is
Okay,
I'm sorry, this is the volume. Excuse me. It's not the size. It's what it's how big, how coarse is the grain. That's what I'm saying. Okay, so with that, we can think about sort of smoothing and saying, well, if this, I'm going to maybe come back here and call this the microscopic. This is the full description of every charge moving around in our system. Okay, and I want to now think about some kind of macro charge density. Okay, which I would obtain by some effective smoothing smearing out. Okay, so this function is some averaging over delta V. Okay, so just loosely speaking, if this was a delta function and we had some width here, which is, I'll just say, delta x is a delta y, a delta z, this is my function, and I'm going to just average over some range and say everything within this course, this delta x, I'm going to say, I'm just going to look at its average value. I'm not going to care about how it's varying over, I'm averaging. So this is an averaging function. Yes?
So it's the averaging over the volume or the?
Yeah, I mean, well, it's the volume, there's a delta x, a delta y, a delta z. This is if this was a 3D delta function, it would just give me back this at its point. But I'm sort of I think about it as like a little Gaussian function in 3D, okay? And the sort of delta x, delta y, delta z is my delta v, okay? So I'm averaging over some range. And, and then the field itself, I would get by the same kind of averaging procedure. For example, the electric field at some point is what the microscopic electric field is from the microscopic description averaged in this way. Okay? So the microfield is what we get from Maxwell's equations given the microscopic description. Okay? Now, without going into details, one can show, this is a shorthand for the professor's too lazy to show you, that so I'll call this the macro field, that the divergence, where now my positions here are the coarse grains, okay? So when I take derivatives, they're over the coarse grains of the macro is equal to 4 pi rho macro. This is, I'm going to defer to authority, C. Jackson, chapter 6.6. Donald, do you have a question?
Yeah. Let's see, so is that F right there?
Yeah.
It's labeled as averaging over delta V. Is it the average that we're multiplying by?
No, I'm sorry. I'm saying this is the function that, this whole thing is the average.
Okay.
So we're taking this thing and we're smearing it out.
So multiplying by F, we find some F that will
Yeah.
multiply by
And
rho.
F has the units of 1 over volume, okay? So if this were a fine grain, F would be a 3D delta function, which is returned back at a point. But because it has some finite extent, it's kind of smearing it out. Okay, does that make sense? Good, okay, so with that said, we can now try to ask ourselves, okay, what is rho macro? Well, we're going to divide the macroscopic charge density into the charges that are free to move around and those that are bound up in the matter. Okay? So we'll divide this up into the free part of the free, that means charges, well, let me write it this way, and then so these are the charges that are bound in matter. Atoms, molecules, solids. And these are charges that are free charges that are unbound. So for example, in the capacitor, the bound charge is the charge that's bound in the gas of air that's between those parallel plates, and the free charge is the charge that's flowing on the capacitors. Yeah, Don.
So are we doing coarse graining so we can work up the fields of matter?
That's what we're talking about. Yeah. It's the macroscopic description. I mean, again, I want to say, in principle, we can define the fields in matter microscopically as well. We do that when we talk about a hydrogen atom, right? We talk about the proton, the electron, and we talk about the field that binds the electron and the proton together. That's a microscopic description of matter. But at a macro description, we average in coarse grain. Yeah?
Can bound charges produce currents?
Sure, and we'll talk about that in a moment. If they oscillate or move as a function of time, then there will be bound current as well. We'll get to that in a moment. You've seen this at your undergraduate level in some way. Maybe you remember it, maybe you don't. But that's how it goes. That's why we're doing it again. Right. So the bound charges will in this case, they're bound together so that the overall, are neutral. If we have an ion, we would put that as a free, part of a free charge, okay? That's sort of the definition, as we're taking it, of the bound charge. Now, let's consider the electrostatic case first. I would write the electrostatic potential as equal to the macroscopic electrostatic potential as, well, I integrate over the charge density associated with the macroscopic, the coarse grain. And that's our general formula for the potential. This is, now we break this up into two pieces. So again, we have, here's our coarse grain. This is our position of the coarse grain. Here's our position of observation. And here's script R, which is the distance from the source to the point of observation, right? That's our usual description that we have of electrostatics bound. Okay? So now, everyone with me? I see you. Yeah. Yes.
Are those added together?
Oh, yeah. Sorry. Excuse me. Okay. Excuse me. There's a lot of puzzle faces that are something confusing. The answer is yes, very confusing. Right. So let's think about this for a moment. What I said here, the bound charge is neutral. So what does that tell us about this, the contribution, how we should describe the bound charge? If it's neutral.
Has no monopole.
It has no monopole moment. And as I heard then, I think what you said now, as dipoles. So the point here is that we should think about the bound charge distribution as dominantly a distribution of, so I'm going to sum over coarse grains So P here is the density of electric dipoles. Okay, that is in the bound charges. So we can think about a molecule. A molecule might have a permanent dipole moment because of the way in which the electron cloud is distributed between the nuclei. Water has a dipole moment. Yeah.
Are we neglecting a potential quadrupole moment, or do we just?
Yeah, we're looking at the dominant effect.
Okay.
Okay. You're right that we should and we do, and if you look at the authority, there is the correction term, but the dominant effect, unless it's not, is electric dipole. Okay. So now I ask you the following question. If I have a little coarse grain here, and it has a differential amount of, in the coarse grain sense, at this position x prime, so in this little coarse grain, there is that much dipole moment, okay? And I ask you, what is the electrostatic potential that I see due to this dipole? What is the electrostatic potential of a dipole? P dot E is the energy of a dipole interacting with an electrostatic field. I'm asking a slightly different question. I'm asking, what is the potential? This is the potential of a point charge. Potential of a point charge is dq over r. What is the electrostatic potential of a dipole? First question, if we don't remember anything in the form, how does it fall off as a function of distance?
1 over r cubed.
1 over r squared. The potential.
Okay.
The potential falls like one, the field falls off like the cube, the potential falls, right? Okay, so there's that. So it's something proportional to the dipole. It falls off like 1 over cube, but dp is a vector. So this whole thing is dp dotted into r hat over r squared. That is the potential of a dipole, okay? Now, we can rewrite this in a very tricky-dicky way, because this vector field here has the same form as the electric field of a point charge at x prime, right? Electric field goes in direction and falls off like 1 over r squared. So this is equal to dp dotted into minus the gradient of 1 over strip dr.
This is tricky dicky.
That's tricky dicky. That's what we used to call President Nixon. All right. So, and dp we just said here, and here's another super tricky dicky thing. This is the gradient with respect to x, but it's equal to minus the gradient with respect to x prime, because this has the same form, but I just changed minus to x prime. So I can write this as dp dotted into the gradient with respect to the prime variables. It's the same thing. Okay, that's just from the chain rule. Okay, so what we have here is that this contribution is d cubed x prime, the integral over the dipole density, times dotted into that. Okay? And now what? Well, we can always play the trick of integration by parts. And everyone remembers, what integration by parts is throwing the derivative from one side to the other and putting a negative sign on it. You don't do u dv, v du. You're not in first Calc 1 anymore. You just know how to deal with a integration by parts. And so what you do in the end is just put the derivative on the other side and put a minus sign, and then you have surface terms. So this is equal to, by integration by parts, minus but we're interested not in what's going on the surface, we're interested in what's going on at the bulk. Okay, so what this tells us, if we put it all together, is that the potential in the macroscopic potential is equal to rho free minus del prime dotted into P, capital P at x prime over x minus x prime d cubed x prime. Okay? And so what we have found by this exercise is that to the degree to which we think about this, the bound charges as being overall neutral, and the degree to which we only take the dipole as the dominant contribution, we find that the bound charge density is equal to minus del dot P.
We're doing surface terms?
Yeah, we're just looking at what's going on in the bulk. Okay? And so, without going into details, I'm going to again appeal to authority. This is true in dynamics as well. I derived it from the electrostatic potential, but it's also true in dynamics. It's just a tedious calculation. It's not too insightful. We get thus the following thing. Del dot E is, we said, was equal to 4 pi the macroscopic, which this is the macroscopic E field, which is equal to 4 pi rho free minus 4 pi del dot P. And so when we put that all together, we get the following. Del dot E plus 4 pi P is equal to 4 pi rho free. And this combination of things, somebody decided to call D. The D field, which is the displacement field. P is sometimes known as the polarization. It's a kind of confusing thing because polarization is, we usually think about the polarization of the electric field in a wave, but it's also called that because you're polarizing the field.
I thought it was the dipole moment.
It's the dipole density. So the polarization is equal to the density of electric dipoles. But it has this name. I didn't make it up. Yes, Tom?
Did you say that the surface terms go to 0?
They're not zero, they're there,
Okay.
but I'm just looking at what's going on in the bulk.
Okay.
So we get one form of the macro Maxwell's equations. So we now have del dot D is 4 pi rho free. Del dot D is still 0. There was no charges that came into that equation. And del cross E is still minus 1 over C dB dt. There were no charges there, so that's fine. But now we need to look at the Ampere Maxwell law to see how that is modified when we're in matter. Now it gets more complicated because, as Omar suggested, there's two kinds of sources now. If we think about the macro current density, again, there's a free contribution and a contribution that's bound up in the molecules, okay? But the part that's bound up in the molecules is now potentially coming from the two different sources. One source of this thing is I'll call J pole. This is the polarization density leading to a current. And then we have J mag, which is magnetic dipoles. So the point here is that if the electric dipole is changing as a function of time, that can lead to a current. So the polarization density, say it's being driven and you have bound charges that are oscillating, they'll give oscillating dipoles. We'll talk a lot more about that. That's one contribution to the bound current. And another contribution is there can be magnetic dipoles inside the matter, and they are going to respond to external fields and give me some overall, overall field, okay? So let's first talk about this term, J-pole. So what we have is that the bound charge density we said was equal to minus the divergence of the polarization, or the dipole density, okay? Which is equal to minus del dot the time derivative if the dipole density is changing as a function of time in some way. But by definition, the bound current satisfies the continuity equation that any change in the bound current is coming from a flow. I mean, any change in the local bound charge density is coming from a flow of the bound current. That's the continuity equation for conservation of bound charge. Okay. So what this tells us is that the bound current density is equal to the time rate of change of the dipole density, okay? So for example, if I have a picture of a molecule as, say, here's, a picture of an electron and a nucleus, which has some net charge E, and there's some spring that is binding them. If I am driving this with some electric field that's oscillating as a function of time, like with some laser frequency, then this will oscillate and there will be current. Okay? Yeah?
You said J bound was a combination of J pole and J mag?
Oh, excuse me, thank you, pardon me. This is the polarization. Pardon me, thank you. Yeah, this is the polarization contribution. Okay, so you can see if there's a bound charges and they're being oscillated, and there's going to be a current contribution. And that current is going to be arising from the time rate of change of the dipole, okay? What about the magnetization contribution, okay? Well, again, of course, there are no magnetic monopoles, so we don't have to worry about that. But we can think about what's called the magnetization or magnetic dipole density, similar to what we just described for the electric dipole density. So let's just first think about magnetostatics. And I'm going to sum over all the coarse grains and this is the average magnetic dipole moment in a coarse grain. Okay. So, in a similar spirit than what we did over here, I have some material, it might have some magnetic properties. There's a coarse grain over here. I'm looking at it over here. There is a position of this guy. There is my position of observation. There's a script R. And I want to know what is, so let's think about magnetostatics. What is the vector potential? Well, so we remember in the gauge where del dot A is 0, we had that the vector potential has a similar form to the electrostatic scalar potential. But instead of the charge density, we have the current density, and we have the 1 over C in these units, okay? So now I want to ask, what is the vector potential associated with the material due to the magnetic dipoles that are inside the material? Yeah?
What's little m sub n, average magnetic?
That's an so what I'm thinking about there is, this is a coarse grain.
Mm-hmm.
Each coarse grain has a little m sub n in it.
Mm-hmm. What's the word after mag?
Displacement?
Nothing. Nothing. It was, I don't know. Well, was there anything that was written in English then? I don't know. Dipole moment.
Okay.
In the coarse grain. Okay. All right. So now I ask you, yeah.
If M is the average, why does it depend on N? If it's an average over N?
And that's not an overgrain, it's at N. In coarse grain, at N. So here it's nth grain, it has.
Oh, I see. So
That's,
the average of each individual grain.
each grain has its own magnetic dipole moment. Every grain, I'm adding up the magnetic dipole moment of every grain, weighted by the strength of that grain. So I take that grain, I average it, and say this is what the magnetic dipole moment of that grain. If this was microscopic, this would be fine grain. That's what we wrote up here. when we added up those fine grains. But I want to get to the punchline here. What is the magnetic, so now I have a little dm here, which is coarse grained, which is equal to the density of dipoles at that magnetic opposite point times coarse grained. And I want to know what is the vector potential at position x given a magnetic dipole dm at x prime.
Would we not just use the expression for a dipole potential?
We do, but it's a vector potential. So we had this expression for the electrostatic potential. What is your guess, if you don't remember what it is? Cross product. Excellent. So we integrate over x prime, and then we have the dm crossed into r hat over r hat squared. Okay? And Vm, we just said, was equal to, so this whole thing is equal to, this is Vm. This whole thing is equal to the integral over all the different positions of the coarse grains, m at x prime, crossed into del prime, using the same two tricky dickies that we used before. Okay? And we do integration by parts, and we get minus the curl of m over x minus x prime plus surface terms, using integration by part. Okay, so what we have found by this exercise, at least in electrostatics, and it's true in magnetostatics as well, that this is equal to minus the curl of m. Okay, so the bound charge density was minus the divergence of the electric dipole density. The magnetic contribution of the bound current is minus the curl of the magnetic dipole density, or magnetization. So now we can put this all together into Ampere's law. So we have that the macroscopic magnetic field is given by this, but we've broken this up into the three pieces. So we have 4 pi over c j free plus the polarization contribution to the current and the magnetization contribution to the current, plus what was called the displacement current. Okay. All right, so let's use this piece of the board again. Sorry.
That was well contained.
Sorry.
I have a question.
Yeah.
Do we have an expression for polarization that I'm just missing?
What do you mean?
For P vector there.
P was defined here. So that is the density of dipoles.
I see.
Density of electric dipoles, M is the density of magnetic dipoles.
Okay.
The amount of electric dipole per unit volume. We never use this expression, this is a formal expression, in the same way that we never write down charge density in this formal way. At the top, it's just the amount of charge per unit volume. This is the amount of electric dipole per unit volume, and M is the amount of magnetic dipole per unit volume. Is that clear?
Yeah, I think so.
Okay. So, I wanted to use this to put this all together over here to say now what we have is del cross V let's see. My signs are something is confusing.
Oh my.
Yeah, this sign was wrong. Okay, you're in luck. I'm gonna have to rederive. All right, Farouk, good move. Let's come back to this because I was too hasty. So let's look at this magnetization, which we said was M of x prime crossed into the gradient of this. Cross products are unfortunate. Okay, so, and there's no 1 over C there, because this is the right units. Okay, so now let's remind ourselves of what is the curl of a scalar field times a vector field. This is equal to, let's look at the ith component of this, is epsilon ijk partial j f v sub k. Right? And so this is equal to epsilon ijk, the partial of j dk plus epsilon ijk f partial j dk. Everyone agree with that? This thus is equal to that tells me that the curl of the f times v is equal to what? It's equal to the gradient of f crossed into v plus f times the curl of v. We agree? This is the curl of v, and this is that cross that. Okay? So this tells me that if I want to, this is the term that's going to give me the surface term, but what I have is the gradient crossed into the vector, and here I have the vector crossed into the gradient. Okay? So there's a minus sign here, so this should have been a plus. I'm going to do the integration by parts.
Should this be
Yeah, I know, I should have done that, damn. Spite myself. Okay, moreover, the current has a 1 over C in it, so this is C times that. So this is correct. So that's going back. Okay, no, I'm not gonna raise it because I'm gonna get in trouble. All right, so. What we have is that the curl of the macroscopic magnetic field minus 4 pi over Cm is equal to 4 pi over C J free plus 1 over C d by dt G plus 4 pi P. That's what's written over here, right? This we defined as a displacement field. And this object is called H, which is sometimes called the magnetic field. I'll explain that in a moment. But we'll call it the auxiliary magnetic field. I'll explain this in a moment. But what we have thus is the final of the macroscopic Maxwell equations. The H dt is equal to 4 pi over C J free plus 1 over C dt, which is called the displacement current. Now this is why Maxwell called it the displacement current. But the displacement current we see has 2 contributions to it. One is to do with the oscillation of the dipoles in the matter that, I'll get to the question in a moment. And then there's another contribution which is coming from E, which back in the day was thought to be the oscillation of the charges in the ether. The vacuum itself was stuff, and that's why the displacement current was considered the oscillation of the ether, which is stuff. Yeah, Evan.
In that second line, is that supposed to be a curl on the left-hand side?
Yeah. Jeez, where's my mind today? It's crazy pants. I don't know. Something is in the water. Maybe it's fluoride. Thank you, Evan. Yeah. All right. So, let's just let me say a few words about this question of H versus B. As some of you know, particularly from in electrical engineering, you always talk about E and H. A lot of textbooks talk about E and H and not E and B. Why is that? It really has to do with the fundamental field is the magnetic field. It's the field that's coming from the microscopic charges. But in the lab, what we really control is the free current, right? So we have some voltage, we have some current. I might have a wire and I control the current that's flowing around it, and it's maybe, they may be wrapped around a nail to make electromagnetic, but I'm controlling the free current. And the free current determines H and the voltage determines E. And this is why electrical engineers always talk about E and H, because they're the things that directly, we don't control the free charge, we control the voltage, and the charges adjust themselves. And that gives us E, where there's a free current determines H. So this is why in electrical engineering, they always talk about E and H. They don't tell you that, but that's why it's done that way. Okay? Right, very good. Now, so we have our macroscopic version of Maxwell's equations. Our reason we want to talk ultimately about the propagation of waves in matter, such as what we call dielectrics, okay? Right, so, typically, in matter, there's a response to the local field. So it might be the case that the polarization density, as in the density of dipoles in some little coarse grain, is 0, but when I apply a local field to it, as there's some field along those lines, then it might be that this guy tries to align. Okay. And I will get some P in some way depending on E. So if we have linear response, then P is proportional to E in some way. And we could write that response as P, the vector polarization, at some position is proportional to E, but maybe the direction in which it's pointing is not necessarily the same as the direction of the electric field. There can be a tensor, okay? And typically this will depend on the frequency of if we have some frequency component that's oscillating, the amount of polarization that's pointing in some direction will depend on the frequency. I'll get to your question in a moment, Donald. Let's see you. I want to just come back to this picture after. Sorry for right. So here is a picture of we had a charge on a spring, and the amount by which it's going to be stretched will depend on the frequency in which I'm driving it compared to the response frequency. Okay. So typically, the amount of polarization that I get at some position will depend on the frequency of component I have. And in addition, the direction in which it points isn't always the same direction which it's pulling, because of their internal forces. You might have a crystal which pulls it in one way, you push it that way, and it goes in a slightly different way. So this thing is called the susceptibility, in this case, tensor, is called susceptibility because it's a question of how susceptible is the system to being polarized. Oh, yeah, question.
Yeah, why does voltage not determine D instead of E?
Because the voltage at the end of the day is determined by the actual forces.
Okay.
And the force is still, the force is Q times E, not Q times D.
Okay.
So the potential is associated with potential energy, and potential energy is associated with forces, and the forces are determined by E, not D.
Okay.
So the charges will adjust themselves. If I put a battery on there, the charges will, I'm not adjusting what the free charges are. They will be what they will be. Whereas if I have a wire and I put on an amp meter and amps to it, I'll have a certain amount of current. That's what I control.
Okay.
Okay, so this susceptibility tensor is a property of the material. Okay, so when we think about the optical properties of materials, we're looking at, for example, what is the susceptibility, right? And the susceptibility will generally depend on frequency. There'll be a different response at a different frequency. Yeah.
So is this susceptibility only a tensor for anisotropic materials, or is that true?
Anisotropic. Absolutely. So if it's isotropic, if material doesn't have a stress or strain to it, or some internal structure of the material, then this will be a scalar. And that's typically what we're going to deal with here.
Is it chi or x?
It's a chi. Okay. So, in general, that would tell me that if I take the Fourier transforms, we'll talk more about that in detail maybe in a few lectures. This is going to be, this is the Fourier domain. The convolution, right? So if this were a delta function in time, then it'd be very fast response, and what the polarization is at that time is proportional to what the electric field is at the time. But if it's got a sluggish response, then the polarization at this time depends on some time integrated version of what that is. So if we have a very fast response, which is to say it's a very flat frequency, it doesn't depend on frequency, all frequencies respond the same, this would look like a delta function, okay?
And then it would just be P equals E.
P equals chi times E. Yeah. Okay, so with that said, we can ask, okay, so the displacement vector in the frequency domain for a given frequency is equal to E at that frequency, and if I have a linear response, then that is equal to 4 pi chi times the polarization. No, times E. Yeah.
So chi is real.
No, not necessarily.
Okay.
No, the chi could be complex, absolutely. And if there's absorption in the material, then yeah, and we'll talk about that. Absolutely. So we can rewrite this as epsilon dotted into E, where epsilon is generally a tensor that depends on frequency, can be complex, which is the identity plus 4 pi chi. And this is known as the dielectric permeability. Yeah.
What is the range of chi? Like, if it's perfectly, instantaneous transmission, then what is chi? I'm trying to get it down on the bounce.
Okay, how big is it? Is it like 1 or 3, or what do you mean by that?
Does it range from if it's perfect transmission, is it 1 or is it C or?
No, it would be 0 if there was no response at all. So if I had something which basically induced almost no dipole, then chi would be 0, and it would look like vacuum.
And what about the other end? Or if it transmitted it created a dipole immediately?
Well, there's two questions I think you're asking. One is about the time response, and one is about the size of chi.
Okay.
Right? So the question of whether or not chi has, and we'll talk maybe, I want to postpone these questions so we talk more about the dispersion to get a physical model. But the main point that one should just get, we'll get a sense of the numbers of this, is that generally chi will depend on frequency, particularly when there are resonances for absorption. Because if I'm near something that has a resonance like this, right? When you force this electron, it responds very differently if I'm right on resonance or far from resonance. And the response function will depend on that. So let's postpone that just for a little bit and we'll get to that. Yeah.
Did you say that linear response is that chi dot E, or the thing on the far left where it's
Linear response
E?
just means that this is a linear function. It just is proportional to chi and not, it's proportional to E.
Okay.
And not E squared.
Okay.
If I had that the induced dipole is proportional to E squared, that would be nonlinear response. And that's called nonlinear optics. And that's physics 560 something, I don't know. So that, but to low approximation, when the forces are particularly, and we'll come to this in a little bit more detail, the electrons are bound very tightly to the material. And to lowest order, I can think about it like a harmonic oscillator. If I pull the thing with a very intense field, then it's very nonlinear. I mean, it goes nonlinear. Yeah.
Do you only see linear response because we assumed the opposite was dipole? Is that why?
No, it's the linear response really is a feature of the matter and the field that we're applying. We'll come to this again. If the fields that we're applying are sufficiently weak, then the response is linear. When we apply very intense fields to the material, they respond non-linearly. Okay?
So this is the same chi from nonlinear optics?
It is.
About the chi
This is
two.
chi 1 as opposed to chi 2, chi 3.
Okay.
This is chi 1 because it's proportional to the first order. It's the same old chi that, for some of you, have that old friend, chi. Yes. So, where are we? Oh yeah, we're here in this class right now. My mind. All right. So, what was I saying? The dielectric permeability. So what we have is that D is equal to, at a particular frequency, is equal to epsilon dotted into E. I guess that's written up there already. Okay. Now, if I have for isotropic materials, chi and epsilon are scalar. Okay. And moreover, if we want, we can say, if we have in a band of frequencies where we have weak omega dependence, then we can basically say, to good approximation, D is approximately some epsilon D. it's really in some band of frequencies where we can just say that it's a constant, but in some range, that's true. And so when that is the case, we can re-express Gauss's law as epsilon dot E is equal to 4 pi rho, which tells me that del dot E is equal to 4 pi rho over epsilon. Okay? This is CGS. Okay. Now, in SI units, you remember we have an epsilon naught there. Epsilon naught is 1, because when I have no material, I'm in free space, epsilon is 1. Okay? There is no epsilon naught. That's a figment of your imagination. Yeah, Tom.
So in isotropic materials, are chi and epsilon real?
No, not necessarily.
Okay.
We'll come to this. The notion about whether it's real or not has to do with the response function and whether or not you can absorb. Yeah. I mean, a piece of glass has an epsilon which is close to 1 at optical frequencies. I mean, an optical fiber, say that's being used for transpacific sending of data, it's pretty damn transparent. Epsilon is damn close, well, but it's not exactly, and it's also not perfectly transparent. There's a little bit of absorption. So it will be generally at the optical frequency, has an imaginary part, which is related to the absorption. Similarly, we can talk about the magnetic case. So in the magnetic case, we define, because we control the current, we define chi the magnetization not proportional to B, but proportional to H. So there's a magnetic susceptibility proportional to H. That's how it's defined, not proportional to B. And so what that tells me is that H, which is equal to 1, or is equal to B plus 4 pi chi dotted into B. No. No. So this tells me that B, the magnetic field, is equal to 1 plus 4 pi chi magnetic dotted into H. And this object is defined as mu. Which is the magnetic No, I got it wrong. This is the permittivity, and this is the permeability. I never remember these terms, I never use them. The permittivity of free space and permeability. Yeah.
Did we just define H in terms of H? Yeah.
No, it is. I mean, it's recursive this way. B is H is equal to B plus or minus 4 pi m, and m is proportional to H. It's the same thing that we did over here. I just wrote it with a minus sign. This is the correct equation.
Right, but in that line up there, we had D on the left hand. And
That's right,
E on
it's
the
just
right
because
hand.
of the way D and H are defined, they're defined backwards from one another, right? Because what we have, really, the equations are more E and H, D and B. This is why it's confusing about what's the fundamental equations. The equations for D looks like the equations for B, and the equations for E look like the equations for H. But what we have here is that D is equal to E plus 4 pi P, but B is equal to H plus 4 pi M. Which means that H is equal to B minus 4 pi M. And M is proportional to H.
Okay, so that equation really defines B.
Hence, yeah, it does, it defines B. So ultimately, what we have is the following.
Is the H on the right hand side supposed to be a complex as well?
They are, okay, they're all complex. So what we have shown is that B is equal to epsilon B and B is equal to mu dot H. So let's just conclude by writing out this for a, everything is complex here, for the case of linear response. So if we have isotropic response with no frequency dependence, then B is equal to mu times H, or H is equal to B over mu. So when we write the macroscopic Maxwell equation, del cross H is equal to 1 over mu del cross B is equal to 4 pi over C J free plus 1 over C epsilon dE dt, because the displacement was equal to epsilon E. And so when we put that all together, we get del cross P is 4 pi over C mu J plus mu times epsilon over C dE dt. Okay, in CGS. In SI units, you may remember del cross B is mu J plus mu epsilon dt in SI. In free space, this becomes mu naught and mu naught times epsilon naught. For us, we got this, okay? In SI units, mu and epsilon have units. God knows what they are, but they're something, farads per meter or something, I don't know. In SI units, what are the units of mu and epsilon? They're unitless. These are dimensionless. Yeah,
And for us, mu and epsilon don't have any relationship to C, right, in CGS?
no, they have nothing to do with C. C was put in by hand after the fact by noticing, as you go back to the very first lecture, the relationships of the forces. There was, in order to be consistent, we needed this factor which happened to be C. The same way that you're taught, oh, the square root of mu naught epsilon naught is 1 over C squared, or 1 over C. It's the same factoid about the relationships between Faraday's law, Ampere's law, Coulomb's law, that they're proportional in a way that has C built into them. They have to be built in somewhere.
So the fact that we learned in physics too, that the permeability, the magnetic and electric constants are related to C is really BS, because they threw it in there after the fact.
That's right. I mean, it would have shown up somewhere.
Yeah.
In some relation of the relative forces, it's in there. Yeah. But in, post priority, we have C by hand, and mu and epsilon are just telling us about the strengths of the response of the medium. And they're dimensionless. Remember, P has the same dimensions as E. And E has the same dimensions as a magnetic field, which has the same dimensions as M, which has the same dimensions as H. All of them have the same dimension. They are charge over charge squared, the charge over distance squared. All right, gang. I'm gonna get my head screwed on, sorry. And
Welcome back into it.
yeah.